Okay, so part 2 of section 2.7 is just 2 more problems where we might see some sort of application of a derivative in the natural or social sciences. So this would be more like economics and business, as you see here. And we have a function called cost, C of x, and it is the cost to produce x number of units. And its derivative is called the marginal cost. So notice that it's a rate of change. Basically, how much does it cost to produce one more unit? Like, what is that change in cost, I should say, like an increase in cost or a decrease. And other places where we see this, you could also you might see marginal profit, you might see marginal revenue. So those are 2 other common places where you might see this in business. So that's actually right here. So didn't need to tell you that, but marginal revenue and marginal profit. So if you're taking the derivative. So suppose we have a cost function C of x. Typically it's not uncommon to see cost functions as that they're polynomials. You might also see cost functions that are rational. That's not super uncommon, but it does mean that often taking the derivative is not too bad depending on what it is. So in a case like this, they just want you to first find the derivative, find and interpret C prime of 100. So the first thing we'd have to do is find the derivative. So go ahead and pause if you'd like and find the derivative and then come back and check it. So I'm just checking my notes here because there's a lot of decimals. So it's a polynomial to the 3rd degree. Not surprisingly, then the derivative is a polynomial to the 2nd degree because every of the terms goes down in exponent by 1. So now we just have to find C prime of 100, and I'm sure you're not surprised to find that that just means to plug and chug. So we're going to take that 100, as I'm sure you're already aware, and we're just going to plug it in. 1, 2, 3, 4, 5. That's the number of zeros. Yeah. 9, and then square. So now I've got 100 that's going in. And then it just becomes finding what we get there. Obviously, one of the important pieces here is to be able to interpret something properly. So once we find that answer, and you can go ahead if you want and find it, you should end up with 0.13. And the idea behind this is that that is money. And so it's really saying that that's a positive, so an increase in 13 cents per item when 100 items are being produced. So we could interpret that as it costs 13 cents, and I mean 0.13 cents is fine, you can say it a couple different ways, to produce one more item when 100 units are produced. So of course this can change based on how many items are produced. So sometimes of course cost is higher when you're producing less, and it's cheaper when you're producing more, and so there's different things to be considered when production is happening, and that's why it's not just a constant increase or decrease depending because of that. So that would be the answer for a typical business problem. So typically not too challenging for most students. Side note. And there are many other applications. So as I say, always make sure you're reading the textbook. It is important that you see different problems. I can't cover everything in the notes. So by reading the book and having the notes, you've got so many resources, you can do it. So now we have the idea of kind of the natural sciences here, this idea of a ripple. So a stone is dropped into a lake, causing a ripple that travels outward at 6 centimeters per second. So the key thing to see about a ripple is that it has a shape. And that shape is what? There we go. So we have a circle. Find the rate the area of the circles are changing after 3 seconds. Round the answer to 1 decimal place. So key things that we're going to need here is we're going to need the area of a circle. And hopefully you remember that it is. So you should know the area of a circle, circumference of a circle. Those are really the 2 things you need to know. It's not too bad. And what we know about the radius is that because the ripples travel outward at 6 centimeters per second, that means that if you picture the circle, it's here, and then that ripple, as the stone hits the water, is coming out and coming out and coming out, and it's doing that at a rate of 6 centimeters per second. So that tells us that the radius of the circle would be 6, and then every second after that, it's of course, when it first starts, it might be 0, but then every second after that, it's increasing by 6 centimeters. So if we know our time being t, so we're thinking about time as t, I can write that t equals time. It tells us that the relationship between rate and time is that every second we get another 6 centimeters on our radius, is the idea. Okay, so what that tells us about the area of our circle is that instead of r, we could write what we found for r, which is that it's 6t, and write it like this. And that would tell us that we have 36 pi t squared for the area of the circle. Meaning we have this relationship between radius and time, so like right now I could put in, it's been 5 seconds, and I would know that the first ripple there was how big that ripple was, because I know how much time has passed. So if we were to take the derivative of this, dA dt, so we're taking the derivative of a with respect to time, which is our independent variable here, we'd be just looking at this piece, and we would use just our basic power rule here and take 2, bring it down. So I have my 36 pi, that's just a constant, so you can kind of think about that or not. And then, so basically the derivative of t squared is 2t. So I'm going to have my 2t, but I'm still going to have my constant there, that's not gone. And so then that's just 72 pi times t. So this is the rate of change of area of the circle with respect to time. So notice it says exactly that. Find the rate the area of the circles are changing after 3 seconds. So we have that rate of change, dA dt. And then at that point, all we need to do is say that we want to find dA dt after 3 seconds. And so that allows us to just do another plug and chug. So obviously this one was a little bit harder, but after 3 seconds looks like this. And you can pause if you want and put that into your calculator and make sure. But if we round it to 1 decimal place, we're going to have 678.6. You should think about what the units are on this, because this is going to come back to us later. But this is the change in area. So area is what kind of units? Squared units. And time here is seconds. So the area of this circle is changing by 678.6 centimeters squared every second. So imagine these circles going out, and you get that 6 seconds. Every second you're moving out 6 centimeters, and then another 6 centimeters, another 6 centimeters every second. And so the area of that circle is getting very, very large. Okay, so now we can just answer the question. The area of the circle is I should say increasing, only because there is the chance that you could have a situation, not in this case because the ripples are going out, but you could have a situation where actually things are getting smaller. So the area of the circle is increasing at a rate of 678.6 centimeters squared per second. So of course that is just a way to, you know, answer a question like that. You could have said the area of the ripples. I said the area of the circle because the ripples are circles, but I would accept multiple things there, so don't worry too much about that. And that is part 2 of section 2.7. Just a few examples of where you might see this sort of thing. So see what you can do with the homework, and good luck.